Welcome to the second lecture of module 3. In this module we are discussing analyzing the batch reactor kinetic data by integral method of analysis. So, before going to this lecture, let us have brief recap on our previous lecture. So, in lecture 1 we considered introduction to batch reactor data analysis, and then we have considered the constant volume batch reactor kinetic data, and then which method of analysis is better, whether integral method of analysis or batch reactor or differential method of analysis. We have discussed among their advantage and disadvantage, and we consider for certain irreversible reaction system we have analyzed by integral method of analysis some of the data. Now, in this lecture we will continue our discussion on integral method of analysis of batch reactor data, and the brief outline of this lecture is integral method of analysis, under which we will consider empirical rate equations of nth order, then we will consider 0 order reactions, we will consider overall order of the reactions from half life, then fractional life method to obtain the kinetic equations, and we will also consider irreversible reaction in parallel. So, parallel irreversible reactions. So, let us start with empirical rate equations of nth order. So, when the order of the reactions or the reaction mechanism are not known for a particular reaction, we can consider a general order of the reactions and find out what is the actual order of the reaction to fit the particular nth order kinetics, and we can then find out the order of the reactions. Now, let us form a general form of the rate equations of nth order, which is minus R A is equal to minus dCA dt, which is equal to K into Ca to the power n. Now, if we integrate after separation of the variables, like we can write minus dCA by Ca to the power n is equal to K into dt, and then if we integrate with the initial and boundary conditions, which is Ca naught to Ca 0 to t, and we will obtain Ca to the power 1 minus n minus Ca naught to the power 1 minus n, which is equal to n minus 1 into kT, and this is valid when n is not equal to 1. So, for n not equal to 1, this integral form of the equation is valid. So, the calculation of the order of the reaction is not straightforward in this case. As we can see, this is an trial and error procedures. So, order n cannot be found explicitly. A trial and error method is essential. How we do the trial and error method? Select a value of n. So, we need to select a particular value of n and then calculate k. So, if we select n, then from the analysis of concentration versus time history of the batch reactor data, we can calculate k. Now, the values of n which minimizes the variation of k is the desired value of k, desired value of n. So, we need to check the value at which values of n which will minimize the variation of the rate constant or rate coefficient. That will be the order of the reactions. We will later analyze this with an example. Now, one curious feature of this rate form is that the rate equations, let me write C A to the power 1 minus n minus C A naught to the power 1 minus n, which is equal to n minus 1 into k T. Now, if you consider n greater than case 1, n greater than 1. If n greater than 1, from this expression you could see that the reactions will never go for completion. So, the reaction will never go to completion. Case 2, if n less than 1, what will happen? The reaction concentration will fall to 0 and then move to negative as you increase the time. So, it further goes to negative. The negative concentration is not possible. So, we should not carry out the integration till a certain time, up to which the concentration of the reactants falls to 0. So, that we can calculate when C A is equal to 0, the time would be T is equal to, T should be greater than equal to C A naught to the power 1 minus n by 1 minus n into k. So, if you substitute T is equal to C A to the power 1 minus n divided by 1 minus n into k over here in this rate expression, if you substitute this T, then you will find that C A would be 0. So, we should not carry out the integration below this, above this time. So, T is equal to greater than equal to C A naught to the power 1 minus n divided by 1 minus n into k. So, as a consequence of this, in the real system what we observe, the fractional order reactions shift to first order reactions, or order of the reactions becomes unity. So, in real system we can observe that fractional order will shift to unity as the reactant concentration depleted. So, this we need to consider while analyzing nth order reaction. Now, let us consider 0 order reaction. As the order of the reaction suggests, if it is 0 order reaction, then the rate of the reactions will be independent of the concentration of the reactants. So, we can write minus R A would be equal to minus d C A dt, which is equal to K, because the rate expression will be independent of the concentration of the reactants. Now, if we integrate this rate expression and we note that the concentration Ca will never be negative. In that case, we would obtain Ca naught minus Ca would be equal to Ca naught Xa, which is equal to Kt for T less than Ca naught by K, and Ca would be 0 for T greater than equal to Ca naught by K. Now, if we plot concentration versus time, so we can see that this is Ca and this is T. So, if we plot for this, we would obtain so this intersection would be Ca naught, that is the initial concentration, and slope of this curve is minus K, and the time at this location would T would be equal to Ca naught by K. If we plot from here, Ca naught minus Ca is equal to Ca naught into Xa is equal to Kt, and that is valid for T is less than Ca naught by K. Now, if we plot Xa versus time, the curve will pass through the origin so it will pass through the origin, and conversion from 0 to 1, say over here it is 1, and so the data, so which you will find that up to time T is equal to Ca naught by K. So, this is the time. You will get a linear equations in case of the 0 order reactions with conversion and time plot passing through the origin, and the slope of this curve is K by Ca naught. And you can note that from the batch reactor data there is some deviation from the 0 order kinetics. So, this is the deviation at higher concentration, deviation from 0 order kinetics. So, it means that maybe you will obtain the data like this. So, that means as you close to the conversion 1 or at higher conversion or higher concentration. So, no, when the reactant concentration falls very low level or the conversion goes higher, you will find that there is a deviation from the 0 order kinetics. This means that the 0 order kinetics is valid up to a certain concentration range. Now, let us calculate the overall order of the reactions from the half life method. So, consider the irreversible reaction, which is alpha A plus beta B and so on to products, and we can write the rate of the reactions for this is minus R A is equal to minus d C A dt, which is equal to k into C A to the power alpha, C B to the power beta and so on. Now, if we write at any instant, we can write this C B by C A would be beta by alpha. This means that the stoichiometric ratio of component A and B, which was present initially, will maintain the same stoichiometric ratio at any time. So, we can write minus R A is equal to minus d C A dt, which is equal to k into C A to the power A into beta by alpha into C A to the power B and so on. So, which we can write k into beta by alpha to the power B, so on, will go to C A to the power A plus B and so on. So, this we can represent as k dash, or and this we can represent C A to the power n. So, this is the general reactions of, we can write in terms of the nth order reaction. So, minus d C A dt would be equal to k dash into C A to the power n. Now, if we integrate this relation, we will obtain integrating for n not equal to 1, we would obtain C A to the power 1 minus n minus C A naught to the power 1 minus n would be equal to k dash into n minus 1 into t. So, now if we define the half life is the time taken for a reactant to reduce its concentration to half of its value. That means, this from here we can write T half would be equal to 0.5 to the power 1 minus n minus 1 divided by k dash into n minus 1 into Ca naught to the power 1 minus n. So, the concentration of the reactants which was initially present is reduced to its half of its value, and the time taken to reach that value is the half life. So, half life is defined with T half. Now, if we plot log T half versus log Ca naught. So, if we take log of this, we would obtain log T half would be equal to log of 0.5 to the power 1 minus n minus 1 divided by k into k dash into n minus 1 plus 1 minus n into ln Ca naught. So, this is of the form y is equal to a plus bx. So, if we plot this, we would obtain an intercept. So, this is of slope of this curve, slope would be equal to 1 minus n, and this is valid for order n less than 1. Now, half life method requires a series of run each at a different initial concentration. Now, if we plot with the same plot with different initial concentration, we would see that when n is equal to 1, we would obtain the curve of log T half versus log Ca naught would be independent of the initial concentration. So, this is for order n is equal to 1. Now, for order greater than 1, we would obtain a curve like this. That means, this is for order n greater than 1. So, numerous variations of this half life method is possible. Let us for instance say for you have large number of components and say we have one component in large axis, say component A in large axis. So, in that case we can write the general expression minus dCA dt would be is equal to k dash Ca to the power A, and this k dash could be k into Cb naught to the power B and so on, and then Cb would be approximately equal to Cv naught. So, this way we can have numerous variation of the fractional half life method, and we can obtain the different form of the integral form of the rate equation, which we could be able to solve for the kinetic data obtained from the batch reactor. Now, let us consider another variations which is called the fractional live method. So, fractional live method, from the half life we can write, say for any fraction, say considered a fraction f is equal to C A by C A naught in time T f. So, the concentration of component A drops to a fraction, any fraction f in a time T f. So, from the half life equations we can write T f would be equal to f to the power 1 minus n minus 1 divided by k into n minus 1 into C A naught to the power 1 minus n. Now, this f we can put any values, it is not 0.5, that is the half life, it can be any value, say 0.8, 0.3 and so on. So, this is an extension of the half life method for any fractional conversion or any fractional change of the concentration at a particular time. Let us consider an example to find out kinetics using the fractional order method. Suppose consider a reactant A which decomposes in a batch reactor as per the following reaction. So, we have reactants A, two products, and the variation of concentration of A at various time in the reactor is measured and given in the following table. So, this is the table which we can see that in column 1 we have time, at different time the concentration of a component A. We need to find out a rate equation using the integral method to represent the data. So, variation of the concentration of A at various time in the batch reactor which is given. This is an example which is taken directly from the Levenspiel. So, once we have the data, the time versus concentration from the batch reactor. So, this is basically the data which is obtained from the experiments. Now, if we calculate log of C A naught by C A and 1 by C A, we can do that from this data. So, log of C A naught is given, which is 10 at initial time t is equal to 0, C A naught is equal to 10. So, the initial concentration is given as 10 mole per liter. So, we can calculate ln 10 by 10 is 1 here, ln C A naught by C A. Similarly, ln 10 by 8 would be equal to 0.2231 and so on for all the other time and concentration. We can calculate the log of concentration of initial concentration by concentration at any time. Now, we can also calculate 1 by C A. So, which is basically the concentration which is initially which was present is 10. So, 1 by 10 is 0.1 and so on for all other concentration at various time we can calculate 1 by C A. Now, these are the data which are given. Now, if we plot the time versus ln Ca naught by Ca, this is we have plotted. Let us guess a first order kinetics. So, if it is first order kinetics, we know the for first order system C minus ln Ca by Ca naught is equal to kT. So, we can write ln Ca naught by Ca is equal to kT. So, if we plot ln Ca naught by Ca versus time, it should give a straight line with a slope of k. So, we have plotted here the column 1 and column 3. So, time versus the logarithmic of Ca naught by Ca. So, as we can see, the data is not fitted with a straight line. So, there is a deviation from the straight line. So, from this we can conclude that this does not follow the first order kinetics. Now, if we consider second order kinetics, second order kinetics. So, if we consider second order kinetics, we can write 1 by Ca minus 1 by Ca naught would be equal to kT for the second order kinetics. So, if we plot 1 by Ca versus time, there will be intercept which is 1 by Ca naught, and from slope we can calculate k, but this also does not fit with a straight line. So, as you can see, it does not follow the second order kinetics as well. So, now consider a general nth order kinetics and find out the order of the reaction. So, to do that, let us plot concentration versus time which are given, and then we can calculate, say consider fractional life method. T f is equal to, say, f fractional converts fractional it reached the concentration to a fraction of 80%. So, that means 0.8. So, f is equal to 0.8. So, which is we can write T f would be 0.8 to the power 1 minus n minus 1 divided by k into n minus 1. So, which we can write Ca naught to the power 1 minus n. Now, if we take the logarithmic as we have done before, it will be log f log T f, which is equal to log of 0.8 to the power 1 minus n minus 1 divided by k into n minus 1 plus 1 minus n into log of Ca naught. So, this is of the form y is equal to a plus bx. Now, if we plot concentration versus time, we obtain the table Ca naught, which is say 10, 5 and 2, and Ca at any time reaches 0.8 Ca naught. So, that means we can calculate this would be 8, this would be 4 and this would be 1.6. So, the time needed Tf, from this graph we can calculate Tf would be from 0 to 18.5. So, it will be 18.5 second. Similarly, if we see from here, it is 59 second at this location. So, from 59 to 82. So, the time change is 59 to 82, which is equal to 23. And in this case we can see from 180 to 215. So, we will take at any two different points and we can see the change in concentration with the time period. So, in this case we can see at this time we have 180 to 215. So, which is equal to 35 second. So, if we calculate log Tf of 18.5, which is equal to 1.27. Similarly, for others it would be 1.36 and 1.54, and similarly we can calculate log Ca naught, which is equal to 1.7 and 0.3. So, now this is the log Tf and log Ca naught we have calculated. Now, if we plot log T versus ln Ca naught, this will fit with a slope of 1 minus n, which is about minus 0.4. So, from the slope of this curve we can calculate that the n is equal to 1.4. So, this is order greater than 1, but it is fractional order. Now, to evaluate the rate constant, we pick up any concentration, say Ca naught is equal to 10 mole per liter and Tf is 18.5 second. So, if we put in the fractional order method, we would get 18.5 would be equal to 0.8 to the power 1.4 minus 1 divided by k into 1.4 minus 1 into Ca naught is 10 to the power 1 minus 1.4, from which we can calculate k would be 0.005 and then unit would be liter to the power 0.4 divided by mole to the power 0.4 into second. So, now we can write the complete rate expression, which is minus R A would be equal to 0.005 liter to the power 0.4 divided by mole to the power 0.4 into S into Ca to the power 1.4, and this has unit of rate is mole per liter second. So, this way we can solve a particular kinetic data which is obtained from the batch reactor, and we can consider different kinetics, and we can solve for the integral form of the rate equations, and finally, we can obtain the rate constant values and order of the reaction, and we can propose the rate equation for that. Now, let us consider an irreversible reactions which is in parallel reactions. Suppose a reactant which is decomposing into two products, that means A to R with a rate constant K 1 and A to S with a rate constant K 2. So, both A and A is producing reactant R and S, both are parallel reactions, and we considered these reactions are elementary reactions. So, in that case the rate of the reactions we can write is minus R A would be equal to minus d C A dt, which is equal to K 1 into C A plus K 2 into C A, which we can write K 1 plus K 2 into C A. Similarly, we can write for the formation of R and S. So, R R would be d C R dt, which is equal to K 1 C A, and R S would be d C R dt, which is equal to K 2 into C A. So, these are the three rate expression. One is the for the reactants, then other two is for the products. Now, this is for the first time we are encountering with the multiple reactions, and if there are n number of reaction components, then a single stoichiometric equations cannot give the concentration profile. So, we need to have n number of stoichiometric equations which would describe the concentration profile. So, for this system Ca, Cr or Cs, all of these alone cannot give the values of K 1 and K 2. So, at least the concentration profile, or we need to follow the concentration changes of the two species to get the K 1 and K 2, and this can be done following two species concentration change with the condition that the total concentration Ca plus Cr plus Cs will remain constant at any time. So, then we can, from this we can calculate the any two concentration profile. If we know, then we can calculate the third concentration from the stoichiometric equation, this equation. So, if we consider the first reactions which is minus dCA dt is equal to K 1 plus K 2 into Ca. So, if we integrate this relation, we would obtain minus ln Ca by Ca naught would be equal to K 1 plus K 2 into T. So, now if we plot this, minus ln Ca by Ca naught versus T, if we plot, so it will pass through the origin and thus from the slope we can obtain k1 plus k2. So, this integral form of these equations will give the combination of k1 and k2. Now, if we divide the other two equations, that is dCr by dt is equal to k1 Ca and dCs dt is equal to k2 Ca. If we divide these two, we would obtain which is Rr and Rs. So, it would be Rr by Rs would be equal to dCr by dCs, which is equal to k1 by k2. So, then we can integrate these equations and we simply obtain Cs Cr minus Cr naught divided by Cs minus Cs naught would be equal to k1 by k2. So, now if we plot Cr versus Cs, then we would be able to get a plot like this. So, this is the initial concentration Cr naught, this is Cs naught, and from the slope of this curve we would obtain k1 by k2. So, if we know from this k1 by k2 and earlier we have obtained k1 plus k2. So, then from these two relations we can calculate k1 and k2 individually. Now, for a typical case of this parallel reactions where A is decomposing to R and S, the concentration profile will look like concentration versus time. So, concentration of A will gradually decrease with so that means it starts with a Ca naught and the profile it is for component A. Now, for component R and S both will increase so it depends on the rate of the individual k1 and k2. So, this will be Cr if k1 is higher and this will be Cs. So, this is the typical concentration profile for parallel reactions. So, thank you very much for attending this lecture and we will continue our discussion on batch reactor data analysis for other reaction systems.